yeah, first of all, I would like to thank the organizer for giving me the opportunity to talk about my research about the quantum phase transition and Ising superconductivity in transition metal dichalcogenide. I'm Justin Ye from University of Groningen. And this morning I will talk about the, first of all, ion gating and its combination with the 2D transition metal dichalcogenide. And then I will talk about field-induced superconductivity in the TMDs, and in particular, Ising superconductivity. And then I will move to some special case called the bilayer and double-side gating. So the general motivation about this work is about making ultra-thin superconductors. So there are many works about the thin superconductivity. The general point is that if you make a superconducting thin film, the requirement is actually not very high, because you are limited by the parameter called coherent length, which is normally very long in the metallic system. So if you make a thin film like a few tenths of nanometer, then you are in the 2D regime. Then you can talk about the ultra-thin superconductor in the 2D limit. But on the other hand, it is if you talk about phase transition, there are some subtle points, because once the system becomes not superconducting, you are entering some other length scale, which is called Fermi wavelength. And in the metallic system, the Fermi wavelength is normally very, very short in the scale of few angstroms. So basically, what you are having is that once you have a phase transition, then immediately from a 2D superconductor you enter a 3D metal. So there are some subtle points there, and I cannot go very much in detail because this is a spin-related talk. But nowadays we have some very good system that means the 2D crystalline system, so that we can study this system with a single layer of a crystal. So then there has been a lot of yeah. Let me have my laser pointer. Yeah. So yeah, you can see my pointer, right? So basically we can actually study them in the crystalline form. So there are many previous researchers about this crystalline form already, and nowadays even we can make monolayer bisco, and they are all superconducting. So this is a approach that we have we can have to first make a very thin superconductor. Another approach is that we can take actually one step back, because if you make a superconductor, you make a 2D metallic system, then most of the time they are not stable. And if we take one step back, we can make a very nice system, first as a semiconductor, but then use a technique called ionic gating to turn them into a superconductor. So the ionic gating, as I've shown here, normally is made by a conventional transistor, but we replace the gate dielectrics with something called ionic liquid. So these are ionic liquid. Then in this particular transistor, we add one extra component called liquid gate. So use this liquid gate, we make a bias, then these ions start to move under the electric field, then we can accumulate carriers on the channel. So this works as a transistor. Of course, one trick you can play if you want to play with spin-related phenomena is that you replace these ions with something contains magnetic element. So one trick we played is that we replace this one with a magnetic ion. So these manganese ion, cobalt. And with this, we can actually gate and control the concentration of these ions on the surface. So we take a non-magnetic platinum, and then we gate with this technique. We can actually induce a ferromagnetic state, as we can see here. If you increase the gate voltage, we start to see an enormous Hall effect and a coercive field. And then in this particular 8 nanometer system, this can be actually quite large for this hysteresis loop here. And considering the field-induced mechanism and very, very large carrier density and very short screening length, this modification should be concentrated on right at the surface. So this should be a 2D ferromagnetic system, and the anisotropy is out of the plane. And take this ion gating, we apply to many different 2D materials. So this is a bit of an overview of the previous work. Then we can actually tune the carrier density in a large amount so that the Fermi surface actually shift significantly. So then in the bilayer and the trilayer case of the graphene, you can actually shift the Fermi surface so much that you start to meet with the second subband, and then you get these features in the transfer curve. And use this same technique. You can also apply this to the layered materials and induce superconductivity. So the typical device is very similar to the previous cartoon. And you apply a gate bias between the channel and a gate electrode somewhere over here. And then you can induce the carrier onto the channel and drive the system into the superconducting state. So this works many years ago already in 2010 in zirconium nitride chloride, and later on we can induce superconductivity in moly disulfide. So this is a technique very, very similar to the transistor, but some special point can be useful to further explore the superconducting state and some spin-related phenomena in the system. One point is, if you consider the carrier density that is in the scale of 10 to the 14th, and if you consider the carrier density and then the Thomas Fermi screening length to be very, very short. So this means the induced carriers are indeed very, very close to the one layer, so that if you gate, you can actually isolate a one-layer electronic structure out from the bulk. So theory tells us if you take a reasonable effective mass of the electron, for instance, 0.5 M0, 90% of the induced carriers are actually accumulated at the right at the surface. So only 10% goes to the second layer. If we go to the phase diagram of the system, this means this layer is very, very conducting in the metallic state and superconducting state, while the second layer is barely approaching a metallic state. So you can well isolate this one from the rest. And if you cool the system down, all the transport is coming from the top layer. But then take this technique, you can actually gate the top layer, and actually you can again gate from the bottom layer. And if they are well separated, for instance, only a few layers, you can actually make a very isolated parallel conduction channel. And this is slightly different from the idea of stacking of multilayers. Here, we only use a natural stacking, but we paint the electronic structure by gating. So you can paint them into different states. One is in the metallic phase, and the other can be in a superconducting phase with different gating. And this is actually quite clear in a system with this kind of configuration. So we can gate from the top and gate from the bottom. And by doing this, we can drive the top layer into a superconducting state, as we can see by applying a magnetic field. We can suppress the superconducting state. But then on the high magnetic field, we start to see some oscillation, right? Then this oscillation actually scales by applying a larger backgate from the back. And if you analyze the oscillation period of these of this feature, you realize that it's coming from a carrier density of 6 times 10 to the 12th, which is well agree with the silicon dioxide solid gate. But on the other hand, if you need to, if you can drive the a superconductivity, then this layer should be in the scale. This top layer should be in a scale of 10 to the 14th. So then this is by doing this, we can separate the electronic structures very well. And then another feature for this ionic gating is that we can actually study the phase diagram phase of the superconductor as a function of carrier density, and we can actually access the phase region that is different from the previous studied phase by alkaline metal doping through the chemical intercalation. And here we can use one sample and apply a gate voltage and so that we can access the different superconducting state. And one feature we can see here is that we actually have a dome-like shape as a function of the carrier density, and this puzzles us for a while. So then we go to a different sample. We go to the monolayer limit, and this is the channel under the PL image of the channel of the monolayer. And then we can see this phenomena actually more obvious. So we have a dome-like shape. Sorry, we have a dome-like shape, and before the dome and after dome, we always have this metallic phase and insulated phase. And after dome, we have this metallic phase, and this insulated phase we call re-entrant insulated, which is very, very counterintuitive, because normally we believe if we apply a gate voltage, we pump carriers into the system, and then system become conductive and become with more carrier, with more gating, and it can be a superconductor, but it never can be insulated again. But the sequence here is start from insulated without carrier. We have a metallic state, superconducting state, and then become metal again and become insulated again. So what happened there is, we can see this very clearly. So first, from insulator, we gate through with more carrier, it becomes more metallic, and it becomes superconducting, and this expansion of that. And then with more gating, it starts from a superconductor, then it back to the metallic state, and then back to very insulating state, go to mega ohm range. And this is and in each case, this superconducting state is actually very, very well behaved. So what happened there is like following. If you apply a gate, especially a very strong gate with ionic gating, you are actually limited by the very poor screening of the 2D system. This is not very serious in a multi-layer system, where you have the second layer that is able to screen. But if you only have one layer, in this monolayer case, we have this ion that is very close to the system, and then the field of this ion start to penetrate and actually forming the trap state. So the physical background, system is like this. We have an insulator, and then we have the bend edge, like a normal semiconductor. And when you put carriers inside, you start to feel this bend tail and start to enter the the real band, then become a metal, and if you go further, it becomes a superconductor. And then, if you gate very much, when this kind of trap states start to form, the donated carrier and will actually be trapped by the trap state, and again, these doped carriers actually gets trapped. And when all the carriers are trapped by those trap state, system again become very, very insulating. So then we have two things. One is the ion gating is very, very isolated. You can isolate the electronic state in a monolayer. And the second message is that if you gate too much, the system again becomes insulating, and the electronic field start to penetrate, and the effect actually go to the second layer. And if you don't have a second layer in this particular case, then you will have a very insulating state. And this actually explains why we have this dome. And if you measure the carrier density as a function of temperature, you start to see that at high carrier density, at high gate, this carrier density start to decrease due to this trapping effect. At a low temperature, you cannot even measure the carrier density by Hall effect because the system becomes too insulating. One subtle detail is here. Here we have some very, very large electric field that actually correspond to the translated electric field into the gate capability of the silicon dioxide. So namely, if we apply a ionic liquid gating, the effect is equivalent to like 2,000 volt through the silicon dioxide. And here, as a function of the gate voltage, this equivalent gate voltage, you can see that at low gate voltage, it behaves very, very nicely as a capacitor. But at high gate voltage, the carrier density starts to decrease, and the decrease is actually a function of the temperature. At low temperature, the decrease is very significant, and eventually the system becomes insulating. So having these two features, we can actually study the system. One point is that because we can isolate the electronic system, and then we can study the superconducting property. And why this is very nice is because we can suppress the orbital effect, because if we apply a B field in the direction along the plane, then we have we can suppress the orbital effect. So then we can study the spin paramagnetism only, and the spin paramagnetism have to can be gauged with the energy of the gap, so that the one parameter we can have is for this spin paramagnetism is something called Pauli limit, and then the Pauli limit is roughly scaled as 2 times TC with a energy with a unit conversion. So with this kind of motivation, we take the system and measure it at a high magnetic field, and we start to see something peculiar. Because if we induce a superconducting state with a very low TC, actually the upper critical field is very, very large. And here, with a TC of 2.3 K, the upper critical field is roughly like 20 Tesla. And by applying 20 Tesla, you can suppress the superconducting state. But if you induce a state with higher higher TC, even apply a 32 Tesla, we are not able to. So 32 Tesla means that we can continuously apply the field there due to the heating effect. Then with this B field, we cannot even suppress the superconductivity completely. So what happens there is a mechanism we call Ising superconductivity. So the brane zone of the TMD, in particular moly disulfide, is having this kind of spin texture at K and K prime of the point of the hexagonal brane zone, and the spin is split at K and K prime point, and they are actually alternating between K and K prime. So if we have a pairing across the K and K prime through the gamma point, and then this blue electron is going to be paired with this red electron, and this blue electron can be paired with this red electron. So then we have a pairing that is across the brane zone, and at each K and K prime point, the pairing is actually protected by very, very strong Zeeman field there. So take the Zeeman field, Zeeman SOC at K and K prime point. This is more or less equivalent to the B field of 100 Tesla. So we have a 100 Tesla protected over here. And then with this very large field, if we apply a external field along the in-plane direction, this external field has to compete with this 100 Tesla. So if we have the Zeeman SOC involved in the paramagnetism, and then this is very well protected. So this orthogonal protection between these between the applied field and the orthogonal protection and the K and K prime point is the reason for this very large upgradeable field. But in our system, we also have a electric field applied in the system, so that not only this Zeeman field, which is actually this configuration, we also have this Rashba interaction due to the electric field applied at the surface. Then Rashba interaction is somehow coupled with the external field when the spin is parallel to the external field in this two cases. And then with increase the gate voltage, we are actually having a larger coupling between them. So with increased gate voltage, we are also having a higher TC. So in our system, for the lower TC, like TC of 2.3 Kelvin, we are actually having a stronger protection. With increased TC, we have a more robust system with respect to the with higher TC, but actually we are having a lower upper critical field due to the increased coupling between the Rashba effect, and increase the coupling between these spin and external field. So this idea can actually be tested with another system, tungsten disulfide, which is having a larger Rashba Zeeman type spin orbit interaction at K and K prime point. So previous moly disulfide is having the 6 millieV Zeeman SOC. For tungsten disulfide, we can have 30 millieV. And with the 5 times larger protection, we are actually having a much stronger superconducting state against the external field. So now I have a superconductivity roughly having 1.5 Kelvin TC. And if you apply a 35 Tesla B field there, you can hardly change anything for this superconducting transition. So if we analyze this behavior, and we can actually compare with the all existing highly protected superconductor. Some of these are these TMDs previously studied, and also niobium diselenide with this Ising type protection, and some heavy fermion that is protected by the Rashba effect. So compare with them, and this is definitely much stronger, and we cannot even measure the more dots because of limitation of the static B field. So this is definitely larger than 10 times the Pauli limit. That's what we can say for these data points. And this phenomena can actually be traced back to some findings in 70s. And at that time, people noticed that if you have a tantalum disulfide, which is having a, nowadays we know this is having a Ising type SOC in the valence band. And if you are able to isolate the layers by inserting organic molecules, you start to see a upper critical field like 6 times of the Pauli limit. So in the modern perspective, present understanding, this is simply realized by having a system that is more isolated between layers. So if you have a longer chain molecule, then this upper critical field actually goes higher. So there are 2 effects. One is the local spin orbit interaction and the layer indice. Because the layer from the layer indice, this K and K prime spin texture actually flip with each other. So this higher blue spin is flipped with this red spin for the second layer. So if you study a bulk, this Ising protection gets cancelled. But then if we can have a mechanism to span the lattice, then this Ising protection start to appear again. So people also study this with the other mechanism. So this is so nowadays people have something called type 2 Ising superconductivity. So here in this moly disulfide, this type 1, so-called type 1, we have a pairing between K and a K prime point, and this is the opposite K and opposite the spin texture. And the same phenomena, opposite K and opposite same texture, can be found in a system that is at a gamma point, not at zone edge, but at zone center. And there, the spin is actually locked with a different orbital if the system has multiple orbital in the zone center. And with this kind of spin orbital locking, you can again put the different spin direction to different K value, and the K prime, K positive and K negative gets paired into a Cooper pair, and then this is again associated with spin, and the spin is protected by the Zeeman type spin orbit interaction. So then, but now another question appears from this diagram. Once you study more than one layer, because in the even in the 2-layer case, spin texture, this spin up and down gets cancelled due to the alternating spin texture that is the layer indice. So if you have a system that is having the layer indice, what will happen if you have this kind of spin texture? So this comes with the theory of the possible superconducting state in a coupled bilayer TMD. We can use the moly disulfide as a model system. So the physics is the following: if you have a conventional superconductor, we have a uniform order parameter. But if we have a layer system, we have the order parameter that corresponds to individual layer. So we have order parameter to the top layer and to the bottom layer. Each of them is with a different phase factor. And this is not important because in normal conditions, if you have spin texture, they are cancelled with each other. But this is not the case once you apply a B field, in-plane B field, and these 2 superconducting states start to be coupled. So if you go to the Hamiltonian, we have the spin indice and the layer indice, and the layer is coupled by this T, this hopping term there. And by applying B field, we add up one more term that is this term to the kinetic energy. And then we can actually form a coupled superconducting state. So namely, we have two layers over here. If you apply B field, they get split in the K space, and then you can have a couple pairing from this to from between these two K and K prime with this couple splitted band. And if you analyze this superconducting state, there's a possibility of forming FFO state. So then we go to the such a system. Then we can actually see that yes. So we can actually make such a system and gate from the both sides. And the effect we are seeing is that compared with the normal phase diagram, the onset of superconductivity actually comes much higher than the onset of the single layer gating. And then this onset is actually 2 times, more than 2 times than a single layer case, indicating some extra pocket is actually present there. So go to the band structure, not only the K point, we also have a Q point at the lower lying band for this bilayer system. So we have to fill all these points so that the carrier density requirement is much higher in this case. And then we go to the upper-critical field. Remember, we have the system. If you make small gating, they are actually coupled with each other, and we are having a trivial system. If you increase the gate, the layers start to be separated, and we start to have a individual. The system start to behave like an individual layer. If we keep gating, the layer again gets coupled because electric field gets penetrated, and again this system become a coupled system. So this is what we can see. So from the weak gating, we have very low upcritical field, indicating the system is coupled. If we increase the gating, we start to see the increase of upcritical field. If the gating is even higher with higher TC, again the upcritical field start to get lowered because the system gets coupled to each other. And this is also the case for single side gating with very strong gate. So with low TC, small gate, this is a very well protected by Ising mechanism. If you increase the gate, the second layer start to be occupied, interlayer coupling becomes strong, the upper field start to decrease. And one small feature here is that we actually have a little kink over there, which is actually predicted by theory. And this the kink actually comes from the competition between the interlayer term, energy scale of interlayer, and the spin orbit interaction. So if we increase the interlayer contribution here, we start to see that the upper critical field gets suppressed, and there start to have a kink behavior. And once this is very big, then the system gets coupled. But if this is very, very big, and this is because interlayer is more or less a constant value if you put these two layers together, and if it is very big spin orbit interaction in the valence band, that is the case of tantalum disulfide and niobium diselenide, and then you don't have this kind of kink behavior simply because this is too big, and you need to have a similar interlayer interaction start to compete so that you can see a kink behavior. This is more so basically with this kind of technique, you can also choose to make a two-layer double-side gating and one-side gating as a junction. Then you can actually have some part is Ising protected and some part is not Ising protected for this upper critical field difference. This is more or less all that I'm going to talk. Then the take-home messages: ion gating is very effective, and especially especially by using the specific characteristics of ion gating, namely isolated electronic system and the tunable interlayer interaction. And then if we use this to Ising superconductivity, we can have the very strong protection and also variable protection by using the interaction. That's all that I'm going to talk. Thank you for your attention.